question 11 is giving us the curve x to the power of x. They used to love asking these questions for like Cambridge and Oxford entrance exams, but it seems to be quite fashionable at the moment. You wouldn't have differentiated this in school in a normal situation, but that it's telling us how to do it at least. So by first taking logs. So we're going to take logs of both sides, and I'm going to take the natural log of both sides. So natural log of y is equal to the natural log of x to the power of x. So I can bring that x down as a multiple, which means we can now use the product rule. But we've obviously got a natural log of y here, not just a y. So we're also going to need to, this is now an implicit function. So in order to differentiate implicitly, remember we pretend the x is a y and differentiate, so that's going to be 1 over y, but then we times by dy by dx. Here we're going to use the product rule. As I said, we're going to pretend, we're going to differentiate the first one and leave the second one alone. Plus we're going to leave the first one alone and differentiate the second one. Differentiating ln x, we're going to get 1 over x. So 1 over y dy by dx is equal to the natural log of x plus 1, which means dy by dx is equal to y times the natural log of x plus 1. But we know that y is equal to x to the power of x. So dy by dx is equal to x to the power of x times the natural log of x plus 1. So, stationary points. Stationary points occur when dy by dx is equal to 0. So that's when x to the power of x times the natural log of x plus 1 is equal to 0. So that's when the natural log of, x to the power of x is equal to 0, or when the natural log of x plus 1 is equal to 0. If we deal with this one first, that's when the natural log of x is equal to -1, or when x is equal to e to the -1. This will never equal 0. So that's not going to give any solutions. So the only stationary point is when x is equal to e to the -1, and we want the full coordinate, I think. No, just the x coordinate, so we can stop there. So it's when x is equal to e to the -1. Okay, for part B, it says that we've got the point A2 on the curve. So I've drawn that here. It says show that A is between 1.5 and 1.6. So we're saying that alpha to the power of alpha is equal to 2. So if we subtract 2 from there, we're going to get 0. And we can now use the sign change rule to show that 1.5 to the power of 1.5 minus 2 and 1.6 to the power of 1.6 minus 2, we're hoping to get one value that's positive and one value that's negative. So 1.5 to the power of 1.5 minus 2 is negative 0.163, and 1.6 to the power of 1.6 take away 2 is equal to 0.121. And we've got a change of sign here. We've got one negative and one positive, so we can then quote the sign change rule and say that since the function is continuous, in other words, there's no asymptotes in the range that we are looking at, the solution to x to the power of x equals 2 must lie between using x now, x between 1.5 and 1.6 due to the sign change rule. Okay, you've got to say both of these things. You've got to say that the function is continuous, and you've got to quote the sign change rule and say that because we've had a change in sign, the root must lie between the two values that we've tested. Okay, it's then given us the iteration formula, or an iteration formula. Xn plus 1 is equal to 2xn to the power of 1 minus x to the power of n. So it wants us to start with x1 being 1.5. x2 is then going to be 2 lots of x1, so 2 times 1.5 to the power of 1 minus xn, so 1 minus 1.5. Now you can put these in on your calculators really quickly, really easily. I think I've done a video on this if you want to look it up. What I'm doing is I'm pressing 1.5 and equals. I'm then going to do 2 times answer to the power of 1 minus answer, and just press equals. That comes out, and we want 3 decimal places, that comes out 1.633. Now because that 1.633 is the last answer, I can now just press equals again to get x3. That's 1.466. And I can press it again and get, this time I get 1.673. Part D then asks us to describe the long-term behaviour of xn. If you keep your calculator with the setup as we had for part C and just keep pressing equals, you'll see that the values, the one that's kind of above 1.5 will head towards 2, and the one that's below 1.5 will head towards 1. And if you keep going, you'll see that it eventually starts oscillating, switching between 1 and 2. So that's what it wants us to say. The values of xn oscillate between x equals 1 and x equals 2. I think it was one mark to say that it oscillates and another mark to say that it's between 1 and 2.